Good evening, sir. Today our group is going to be presenting on the topic Mastering Atari Games and Beyond, a journey from deep Q learning to adaptive recurrent networks. Today we are going to be covering two research papers, the playing Atari with deep reinforcement learning and deep recurrent Q learning for partially observable MTPs. So I'm going to be covering the first paper, playing Atari with deep reinforcement learning. So the main aim of the paper is that the paper presents the first deep learning model which was successful in learning control policies directly from high dimensional input in the form of raw pixels. That is, image snippets of image at various timestamps. This was achieved using deep Q learning, using convoluted neural networks to create Atari games. The paper presents the results of 7 Atari games. A lot of other methods reinforcement learning have been used till date, but they all comprise of hard engineered features which were manually created. Uh, this paper presents a deep Q learning method um, which did not involve any hard engineered features, and the network itself learned uh, extracted features and which were used to learn the model. So the introduction of the paper. So we know that earlier attempts to train agents using visual and auditory inputs have relied on handmade features. Yeah, these attempts have heavily relied on feature qualities. So like people used to themselves extract like qualities and each feature was dependent on the game and the setting in which the model is being used. So yeah, this paper covers and takes care of this challenge. And the challenges of RL in deep reinforcement learning is that deep learning has made possible high level feature extraction in other areas such as computer vision and audio recognition. So why isn't it possible in RL? So the first setback we have to face is RL only uses scalar rewards and delayed and noisy rewards and sparse rewards. So like a lot of episodes and a lot of steps have to be taken, and we receive a very sparse reward which does not convey a lot of information at a very delayed time. So we could have played T steps and received the reward of the first step after T steps. And that the reward is also a scalar quantity which does not convey a lot of information. And the second point is data samples in computer vision and auditory recognition are not related to each other. And but in reinforcement learning, as you know, the model itself affects the data on which the model is being trained on. So and the data which is being collected also is very highly related with itself. So the results also affect the data on which it is being trained. The distribution of the data is also being affected. So we are going to tackle each of these problems in this paper. The first scalar rewards is being taken care of by the network itself, and the data samples, the high correlation of the data samples is being taken care of technique that we use, which is called experience replay buffer, which we'll see in detail later. So yeah, the paper presents a model which designs a single neural network, and this neural network can be trained for each game separately with slight adjustments based on the features of the game, but the core network remains the same. So we will cover the background of the whole setting. We have an environment which we have to call the Atari emulator, and we have the action space which will consist of all the control actions uh, which can be taken in the game. Like for instance, in Pong, the actions that can be taken are like staying steady or like going up, going down, or like no action at all. So three actions in this case. And image of a state, so at any point in the game, uh, like we will capture the state via a photo, which is represented as a vector form, uh, 84 by 84 in grayscale. So this is how we represent the data, and the reward is the total number of points that the player and the opponent gets. So the reward in this case can be zero, which will be zero for most of the time, and will be plus or minus one rarely when one of the person misses the ball. So now we look at some of the main formulas which are related to the setting. So yeah, the reward is denoted by small rt. The objective of the entire uh, training model is to maximize the total reward, which is denoted by uh, gamma raised to the power t dash minus t into rt dash, which is the delayed reward, sum of the delayed rewards of the entire episode. The second is the action value function, which the maximum of which is denoted by max over pi of expectation of the reward, depending on the state and the action taken, and depending on the policy. So varying the policy, we get the maximum of, we take the maximum over different policies. We get the Q star of SNA. And the Bellman equations, as we know from classwork, presents the expected reward plus gamma times max of Q of S dash comma A dash uh, over the various states in that the environment goes from S comma A to S dash. So the basic idea behind the many algorithms are algorithms used to estimate action value function is like in the value iteration method, in which we used to iterate over value the value function repetitively to get the final value function v star. This similar method is used in a lot of RL policies for the action value function as well, in which we iterate uh, over q of I plus 1 using this formula. But in our settings and most of the settings, this is not practical at all because of the very large number of states and action function values, especially in continuous settings. So to tackle this, we use functional approximators, which is like with the q function of s comma a, which is dependent on theta. So we use weights to represent and vector form to represent the expected value of the q function over different SNAs. So this can be used. The approximator can be of two types: linear approximator and non-linear approximators. In most of the cases, we will use function approximators, but in neural networks, uh, example, the different activation functions like review, we can get non-linear approximators using different weights theta. And now find the absolute value, final value of the q function. We minimize the loss function, which is denoted as expectation of qi minus q of s comma a comma theta I squared over different SA depending on their probabilities, which we have seen in class as well. So the target of the iteration I, yeah, so phi I is equal to, like, depends on, yeah, phi I in this formula is calculated with this equation, and P of S comma A is the probability distribution of different S comma A. So taking the gradient over the loss function, uh, we get this equation, which is used by the stochastic gradient descent method to solve for the theta vector, which will help us calculate the value of Q star. So, like, taking the overview of this algorithm is model free because we taking the samples directly from E. We are not calculating P of S comma S dash. The second, the policy is off policy because we are taking greedy strategy to calculate the next action. Uh, what is this Q? It's calculated over maximum of maximum value over A. Third is that the algorithm is epsilon soft. That is that every action has an epsilon by number of actions probability of being selected. So we are using epsilon greedy policy to select the action. That is 1 minus, we will select max over A Q action with 1 minus epsilon probability, and any of the n actions used by epsilon by n probability. So yeah, so we have seen from the algorithm that the algorithm is model free, off policy, and epsilon soft. So from theory, we know that model free, nonlinear function approximators, and off policy methods. These three together are known as a Delphi triad from the Barton-Sutton book. And in most cases, the network may diverge. So we will not find the optimal policy in most cases. So to take care of this, we make our experience replay buffer, which stores different experiences at each time step. In our problem for the games, the experience replay buffer has a size of 1 million. And it stores the recent 1 million steps at each time step. The one value of the experience replay buffer is denoted by the state action, the reward obtained, and the next state achieved. And data set is denoted by the capital D, which stores the last n tuples. So it is like a clockwise that after we perform the next step, E1 will get removed and E of n plus 1 will get added. So yeah, in most cases, we apply mini batch updates, samples. Uh, this helps reduce the variance of and the dependence on one action, so that we get a more distributed gradient descent, and the probability of divergence is very less in this case. Yeah, so in our problem, the selected samples are denoted by a phi function that is at each. From every image, we perform a phi of xt using other values from the replay buffer to form the like we get different value which is denoted by s of t, and we perform all the steps. This denotes the state because every normal image does not store a lot of information. So phi of xt in our problem setting combines the last four images. So which also gives us a more information about the state, because if we like look at it in normal state in like the Pong setting, we have no idea where the uh, opponent is going or where the ball is traveling. The ball will be traveling in this direction, this direction. So we take the last four images and perform an operation on them to get our final state, which is used to perform on the proximate on all the functions upon. Yeah, so the advantages of using this phi function is that each step of expression using many weight updates, and learning from only one sample is inefficient. Randomization breaks these correlations, and the variance of updates also decreases. In many cases, like the it is possible that the the function oscillates between two states. Randomization prevents that, so divergence also reduces, and in almost all cases the function converges to a value. So coming to our model architecture, before that we will look at the deep learning algorithm. So yeah, the replay memory B is initialized to capacity n, which is approximately 1 million in our setting. Initializing action value function with random weights, and for episodes and for m episodes, we initialize a sequence S of with the image of x of I. The x of I is pre-processed to phi of 1, and for the entire episode, we do the action selection policy, greedy action selection policy, epsilon greedy action selection policy. Then we execute the action in the emulator and observe the reward and the next state, next image received, and we get the next state and reprocess it, and we store the transition in the replay buffer. Yeah, for now, for applying the uh, stochastic gradient descent to change the values of thetas, we set the value of y depending on whether phi of j plus 1 is the terminal state or not. And then after this, we perform the gradient descent on yj minus q of phi of phi j comma a comma theta according to the previous equation that we have seen above. Yeah, so for this, we usually take 32 mini batches, or we randomly select 32 data sets, data points, and take the average of them, and then we perform the gradient descent on them to like average out, and this reduces the variance and helps convergence of the formula. Random checking data also helps in like, making many uses of like old data, so that if we have like a policy, the data in this experience buffer is not uh, will not be related to this policy. So we get we solve our issue of that we had discussed earlier. Yeah, that the data samples are highly correlated. So this helps in distributed data sampling. And yeah, so performing for this, we usually have like an actor critic method, which in which we freeze one. We have two queue networks. We freeze one queue function, and and for like a certain number of steps, in most cases, it is 1,000, so that we can the target is not doesn't change as well. So that when we take the gradient, we only take the differential of the 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 value that is getting closer to the target. Otherwise, the target will also change, and it won't guarantee convergence. So this is like the basic idea of the algorithm that we are going to use in our model. Uh, so for the problem given in the paper for solving for the Atari games, uh, in general, a normal Atari game is of 200 into 160 pixels with 128 color palette. This was pre-processed down to an 84 into 84 region of image, and we also applied grayscaling to reduce the number of input features so that we can train the neural network more easily. And generally, phi function includes any random states, but in our case, we use the last four frames. Yeah, and the Q network is denoted by is like can have like a view of this. So the input consists of all the states, and the output consists of all the actions. As we have to calculate, we have to take the maximum over all q of s comma a. If the neural network had only one output, we would have to like iterate over n actions. We would have to find use the network over n times to find the value of every s comma a pair, keeping the s constant for every action. So we have n output nodes for n actions, and we will take the max which and the output of each action is the value of q of s comma a, and we take the maximum for all these values to get a final value. Yeah, so the only state is input is considered the input. The separate output node for each action in it. The output is produced is the predicted q value. So in one pass only we can find all the values of q of s comma e for any given s. So for the training of the model, the phi is denoted by 80. The input is 84 into 84 into 4 image, many nodes. We have three hidden layers. First is a 16, 18, 8 by 8 pillar with 4 stride. The second hidden layer consists of 32 4 by 4 filters with 2 stride. And the final layer is a fully connected 256 rectifier unit. And the output layer consists of one output for each action. And for over the 7 games, the value of number of actions vary from 4 to 18. So this is the overall problem setting. So now coming to the results which were obtained in the experiments and the results. So from the experiments performed, yeah, and also we trained for over 10 million steps, and the value of epsilon was also anneals linearly. Like it was first taken to be 1, and gradually it was reduced to 0.1 over 1 million steps. And yeah, it was then kept at 0.1 for the remaining 9 million. And we also had a K frame skipping method that for K inputs we did not take any action, and after every step we used to take an action. This helped. This was the value of K was taken to be 4 for most games, except for a few exceptions like Space Invaders, an Atari game, which we had to use K is equal to 3. This was helpful in taking more data and like performing for more number of episodes. So looking at the results, we see that for most of the games, the general trend in the average reward during the training session, the average reward kept on increasing. The variation is quite high, but in general, the the net reward kept on increasing. Another estimate for the was taken to be the average of Q, random Q values of different states, which gave a more stable output and showed that the network was learning over time. Yeah, and different the DQN method was compared with other algorithms which had been previously implemented like random and SARSA, and we can clearly see that DQN outperformed all of them over all the 7 games. It was also tested next to the human average human scores, and it outperformed them in many of the games, like you can see in Breakout and Enduro and even Pong. Most of the games in which DQN was able to outperform humans were which which did not require a lot of strategy. Like in many games which we had to look a lot of steps ahead, the DQN was not able to work very well in, which is like yeah, it's very understandable. So this paper introduced a new deep learning model for reinforcement learning and demonstrated its ability to master difficult control policies for Atari 2600 computer games using raw pixels as input. We also rendered a variant of online key learning that combines mini batch updates with experienced replay to ease the training of deep networks of RL. And in 6 of the 7 games, the Q network was able to work on the games and perform well without any adjustment on the hyperparameters and the architecture. So yeah, thank you so much.
Hi everyone, myself Avinash, and I will be giving a brief overview about deep recurrent queue learning for partially observable MDPs. Like first, we will know what exactly is partially observable MDP, and then we will discuss the shortcomings in traditional DQN, and then we will further proceed with the other topics also. Like what exactly is partially observable MDP? A partially observable Markov decision process is an MDP with state uncertainty, meaning we can't know the true states, only a belief about the true states using observations. Like a POMDP is described by 6 parameters. Like if we remember in traditional MDPs, we had 4 parameters: state space, action space, transition functions, and reward functions. But in case of POMDP, we will introduce 2 new parameters also. First one is observation space, and second one is observation function. Observation space. The observation space represents the finite or infinite set of all the possible observations that the agent can receive from the environment. Like for example, in a robotic scenario, the observation space might include sensor readings such as distance measurements, camera images, or other environmental cues. And talking about observation functions maps the underlying system states to observations in the observation space. It defines how the agent's observations are generated based on the true states of the environment. Now we will discuss the nature of Atari games. Like, is it POMDP or is it typical MDP? Atari 2600 games are typically described by console's 128 bits of RAM, yet players are only able to see the console-generated game screens. And due to this disparity, a single game screen often fails to convey the complete game state, like the previous state, like the position of the ball, velocity of the ball, etc. And DQ1 addresses this by incorporating the last 4 game screens into its states representation, thereby transforming many POMDPs into MDPs. But the challenge lies in introducing partial observability without reducing the number of input frames provided to DQ1. Like we can introduce partial observability in Atari games via flickering, like introduction of flickering in Pong POMDP. Modifications of the classic Pong game, whereas each time step screen is randomly fully revealed or like it's hidden with a 50% probability. Like with half probability, screen is visible to us, and with half probability, screen is hidden from us. And this probabilistic obscuring induces an incomplete memory of observations necessary for Pong to qualify as POMDP. And now we will be discussing the shortcomings in traditional DQN. Like in the paper 1, we discussed about the DQN and its architecture, and now we will be discussing the shortcomings in it. Like as we know, we have limited memory access in case of DQ1. So DQ1s have a fixed memory capacity, often restricted to the last few game screens. Like in our case, it was 4 game screens, and hindering their ability to effectively capture long-term dependencies in game states beyond a certain time frame. Like the traditional DQ1 is pretty much sufficient in case of those games like in which there is lesser time dependencies. But if there are games in which we need a longer time dependencies than traditional DQ1 fails to do. And now we will be discussing an improvement over traditional DQ1, that is DRQ1, Deep Recurrent Queue Learning Network. We explore the concept of Deep Recurrent Queue Network, which is a combination of RNN and DQ1. The idea being that RNNs will be able to retain the informations from the states further back in time and incorporate that into predicting better queue values and thus performing better on the games which require long-term planning. And now we will briefly discuss about the architectures of a typical DRQ1 setup. As we can see in our DRQ1 architecture, first we have an input image and then three different convolutional filters, and finally these are stitched by a single LSTM layer which outputs queue values. The modifications which we introduce in typical DQ1 architectures are DRQ1 retains the basic structure of DQ1 but replaces its first fully connected layer with a recurrent LSTM layer, allowing it to capture temporal dependencies. And as I said, the input is in the form of an image of size 84 cross 84, which is passed through three different convolutional layers. Like we can see the images of the outputs of the different convolutional filters. And now coming to the the use case of different convolutional filters. Like the first layer mainly notices the paddle, like the position of the paddle, while the second layer tracks the ball movement and its interaction with the paddle. And finally, the third layer monitors complex interaction like ball speed and direction. As we can see, like here, the first layer is tracking the position of the paddle, and the second filter is actually tracking the ball movement. And finally, the third convolutional filter is monitoring the relative movement of the paddle and the ball both, like the relative positions of both. And now, our architecture, like describing our architecture, like it has compensation for limited convolutional detection, and also during training, DRQ1 runs from the past 10 frames, but both DQ1 and recurrent DRQ1s have access to this history, helping them understand the game's context better over time. And now we will be comparing the results of DRQ1 and DQ1 algorithms over different Atari games. Like we will see that both the algorithms have similar kind of performance in case of MDPs. Like if an Atari game is following an MDP, like it is a Markov decision process, then both the algorithms have a similar type of performance. And it is visible, like we will be comparing the two different Atari games. First one is Frostbite and second one is Beam Rider. Like as we can see in the Frostbite games, DRQ1 performs better than DQ1. Like after 15,000th episode, like it is able to learn a stable policy through which it can maximize its reward. And in case of Beam Rider, DRQ1 fails to compete with DQ1. We can see a significant drop in the reward in case of DRQ1 in comparison to DQ1. Like we can see Frostbite performance jumps as the agent learns to reliably complete the first level. Now we will see the generalization of a typical MDP Atari game to a POMDP. In POMDP environments, DRQ1 retains more performance than DQ1 across all levels of flickering, showcasing its robustness against missing information. This suggests DRQ1's superior ability to generalize from standard MDPs to POMDPs at evaluation time. Like here in this graph, we can see that as we increase the observation probability, like we can see the initially when partial observability was more like with higher probability we had a blank screen, then there was significant gap between the performance of dq1 and drq1, like drq1 was much ahead with respect to dq1. But as we increase the observation probability, like we proceed more towards a classical mdp, then both the algorithms have similar type of result. And now we will be concluding the DRQ1 architecture. Like DRQ1 demonstrates its efficacy in handling partial observability by integrating informations across frames to detect relevant features. And also we can see DRQ1 outperforms DQ1 in handling partial observability and generalizing across different levels of observability. It shows, but as we see in case of typical MDP, it shows no systematic advantage over DQ1. And now we will be discussing the future prospects, like the implementation part of DRQ1 architecture. Like the first application that we can see is smart traffic management. Like in this case, we will develop a DQN based traffic management system to optimize traffic flow, reduce congestion, and minimize travel time in urban areas. And another future prospect of DRQ1 architecture can be real-time strategy building in AI games also. And also we can incorporate DRQ1 algorithm in case of autonomous drone navigation. Like we can implement a DRQ1 based navigation system for autonomous drones to navigate complex environments, avoid obstacles, and perform tasks such as package delivery and search or rescue missions. Right now, I will conclude this discussion. Thank you. And now coming to the final review, like we will be implementing the code for DQ1 and DRQ1 algorithm, and we will be comparing both the algorithms for different set of Atari games and plotting their results, like which algorithm is giving better rewards in case of which different Atari games. And also we will be analyzing the third paper on deep RL, which introduces a new neural network architecture called dueling network for model-free reinforcement learning. It will separate the estimation of state value function and state dependent action advantage functions, and this separation will allow for more efficient learning across actions without altering the underlying reinforcement learning algorithm.